Okay, so here's an interesting do now. Find the sum of the numbers from 1 to 100. Try to do it without your graphing calculator or out any calculator at all. Okay, and obviously there's an easier way to sit there than add up 1 plus 2 plus 3 plus 4 plus 5, etc. all the way up to 100. Pause the video for just a second and see if you can figure that out. Okay, so now that you've tried to see if you could actually add up the numbers from 1 to 100 with some sort of a pattern, maybe some of you recognize that if you start pairing numbers together, sorry, I should put that extra plus in there, you will see that if you add up 1 plus 100, that adds up to 101. Oops, 1. And if you add up 2 plus 99, that adds up to 101. And if you add 3 plus 98, that adds up to 101. And if you keep going and keep adding up these pairs of numbers as you move your way in towards the center of that pattern, you will see that they always add up to 101. So here's how do we use that to figure out the sum of all these numbers? Well, obviously you can see that we're doing 101 over and over and over again. How many times are we doing it? Well, since we're pairing numbers together and there were 100 numbers to begin with, there are 50 pairs of numbers. Therefore, 50, 50 is the sum of the values from 1 to 100 without having to sit there and add them all together. Okay, that's going to be an example of something that we're going to look at tomorrow called an arithmetic series. It takes an arithmetic pattern, notice to get from 1 to 2 and 2 to 3 and 3 to 4. You're always adding by 1, but it takes the pattern, instead of writing it as a pattern, 1, 2, 3, 4, it starts adding the terms of the pattern together. That's what makes it a series instead of just being a sequence. But again, we're going to come back to that tomorrow. One of the shorthand ways of representing a series is to represent it in something we call sigma notation. So that's what we're going to be talking about today, sigma notation. Okay, so sigma notation is using this shorthand Greek symbol called sigma to be able to represent a sum of numbers that have a specific pattern. So you can see in this situation, if I start with the number that's in the bottom and I plug that into this formula right here, 1 as n is just 1. Now I'm going to continue to add all of the numbers that are whole numbers all the way until I get to the very top number of 5. So therefore I'm going to plug in 2 in for n, and that's where I get 2, and 3 in for n, and that's where I get 3, and then 4 in for n, and that's where I get 4, and finally 5 in for n, and that's where I get 5, and then I can write that as a sum. This is that sigma notation expressed as a sum. Okay? So sometimes you're going to represent it as a sum. Sometimes you're going to actually, add those values together. Okay, right now we're just kind of, doing some practice. So if you take a look at example number 2, once again, I'm dealing with this sigma notation that's telling me to add terms together. This is the pattern that I'm plugging numbers into. You always start with the number that's on the bottom of your sigma, and you use every single integer all the way up until you get to the top, and you plug those all into that formula n cubed. So that's where I get 1 cubed, 2 cubed, 3 cubed, 4 cubed. And that's the sum of my numbers. Okay, you're just representing it as a sum. If you take a look at the next example, this one is not starting at 1, still okay. You're still doing a sigma. What rule are you plugging into? You're plugging into 2i. You're starting with 4, so notice that I start with 2 times 4. Then I plug in 5, then I plug in 6, then I plug in 7, and finally I finish by plugging in 8, and that now gives me my pattern written as a sum. Okay, so that's what we're going to do right now. We're going to just do a little bit of practice representing each as a sum. Honestly, you don't even have to evaluate them right now. Okay, we're just doing practice. Okay, so for my first term, it's going to come from doing 4 times 1 squared plus 4. That's my first term. Then my second term is going to be 4 times 2 squared plus 4. Okay, and I'm going to keep adding terms together. 4 times 3 squared plus 4. 4 times 4 squared plus 4. And finally, the last one is 4 times 5 squared plus 4. Okay, if you did actually want to write this as a simplified, as simplified terms, you would see that this comes out to be 8 plus 20 plus 40 plus 68 plus 104. Okay, and again, right now, you're just writing each as a sum. You don't actually have to evaluate it. Okay, so let's try another example. If you take a look at example like number 4. Let's go to question number 3. I like one that's not necessarily always starting at 1. So you're starting here by plugging first in 4. So I'm going to have 20 minus 4 squared. Okay, okay? Then you're going to plug in whatever the next integer is, 5, 6, 7, 8, all the way until you get to the very one at the top. Okay, so 20 minus 5 squared, 20 minus 6 squared, 20 minus 7 squared, 20 minus 8 squared, and then 20 minus 9 squared. Okay, and now you have that expressed as a sum. And again, if you wanted to write it in a more simplified form, then you can write it as, what does that one come out to be? 4 minus 5 minus 16 minus 29 minus 44 minus 61. Okay, so what if you had to actually add the terms of that series together? If you take a look at the next section where it says evaluate each series, that's when you actually take the terms of the sigma that you found before and then you actually add them together. That's the only difference. So a lot of times maybe you want to first start by writing this out as a sum. You know what I mean? So you're going to start by saying, okay, I have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 and then 3 times 5. Okay, and you can go ahead and you can plug that right into your graphing calculator. I would say plug it all in one step so you don't make any mistakes. And this time you have to finish by writing your final answer as 45. Okay, if you take a look at the second example, we'll do the same thing, only this time again we're starting by plugging in 3. So I'm going to have 30 minus 3 plus 30 minus 4 plus 30 minus 5 plus 30 minus 6. And as I add all those together, that's going to come out to be a value of 102. Okay, so that's the basic idea of sigma. Again, it's a shorthand representation of a sum of terms. And depending on if you have to write it as a sum or you have to evaluate, you either leave it as a pattern of numbers being added together or you actually come up with what the value is when you add it all together. So sometimes you want to take a specific pattern you're given, a series, and write it in this sigma notation. And what you're going to do is you're going to rely upon your formulas for an arithmetic or geometric sequence, and you're going to use that to create that sigma. So if you look at the example we had in the do now, remember we were adding 1 plus 2 plus 3 plus 4 all the way up to 100. Okay, and let's think about how can we rewrite this in sigma notation. Okay, so you're always going to start by writing a sigma. Now, if you remember, when we did these patterns, you always had a sub 1. You plugged in n equals 1 for the first term and n equals something to get the last term. Well, I would say always start by putting n equals 1 on the bottom of your sigma when you have to write it using your arithmetic or geometric rules. Look at the pattern of numbers you have. 1, 2, 3, 4, etc. This is an arithmetic pattern because you're constantly adding by 1, so that's your common difference. If you needed your nth term rule, that would be your first term, which is 1, plus n minus 1 times your common difference, which is 1. I mean, you can leave it just like that. If you want to simplify it, you can make it 1 plus n minus 1, or just n if you prefer. But I'm definitely okay if you leave it in an unsimplified format. So if you now put that inside your sigma, 1 plus n minus 1 times 1, or just n. Again, either one would be fine. Now what you have to do is you have to finish by putting in what n did you plug in to get to the last number. Now if you had actually written this in simplified form, it might be a little bit easier. Oopsies, sorry. Because if you take a look at the fact that if you had to evaluate the values of n, just n, there's no pattern, it should be easy to see that the last one came from n equals 100, okay? Okay, so you're plugging in every number from 1 all the way up to 100, and when you get each of those numbers from 1 all the way to 100, you add them together, and this is now representing the this is now the sigma that represents this situation. Okay, so if I go now to the next two questions, it says rewrite each sum in sigma notation. Okay, so first things first, let's look at this pattern of numbers. 5, 11, 17, 23, etc. Okay, so if you take a look at this one, you can see that you're constantly adding by 6. That's why it's an arithmetic pattern. If I write a rule for this arithmetic pattern, it's my first term, which is 5, plus n minus 1, times my common difference of 6. So when you create the rule for sigma, You want to always start it with n equals 1 because based on what we use for sequences, we always start with n equals 1. We'll talk about how you can find the upper bound in this situation in just a second. The a sub n rule that you create without actually writing a sub n goes inside the sigma, so 5 plus n minus 1 times 6. And now we have to figure out what n did we plug in to get our very last term. So the easiest thing you could do is set your a sub n rule equal to 53 and solve to get that n value. So if I take 53 and I set it equal to 5 plus n minus 1 times 6. So I'm going to solve this a little different than I'm sure you expect. I'm not going to distribute. I'm going to start by minusing 5 from both sides, which comes out to be 48. If I divide both sides by 6, I get 8 equals n minus 1. Or if I add both sides, 1 to both sides, I get n equals 9. I now know that 9 has to be the n at the top of my sigma in order for my last term to be 53. Okay, and now I've expressed this in sigma notation. Okay, so if you go backwards and you want to check this out, maybe take the pattern you have inside the sigma, put that into y equals in your calculator, look in your table of values as you plug in all the numbers from 1 to 9, and make sure they match what you're seeing inside of this series right here. Obviously, you know that not all patterns are arithmetic. Sometimes you have patterns that are geometric. So take a look at question number 2. So again, start by identifying what kind of pattern that it is. Okay, so as I take a look at this, I can see I'm constantly multiplying by 1/2. If you can't see that, remember that when it comes to geometric, if you take a number and you divide by the previous number, so notice 20 over 40 would be 1/2. 10 over 20 would be 1/2. So 1/2 is my common ratio. For a geometric series, you start with your first term still, only this time you're multiplying by your common ratio raised to the n minus 1 power. So when you set up your sigma, you're still going to start with n equals 1, because remember, you always had a sub 1 as your first term. We'll talk about how you get the upper bound in just a second. Your a sub n rule that you create for that pattern without the actual a sub n goes inside the sigma. And now to figure out what the n value should be for the last term, take the last term you have and set it equal to the pattern for that particular situation, and then solve to get your n value. This is interesting because this is going to pull in some stuff from our previous unit. So I have 5/8 equals 40 times 1/2 to the n minus 1. So now you can use logarithms if you'd like. You can use, if it's possible, to get both sides be, the same number being raised to a power. Either one of those processes will work for you. Or, obviously you can use your graphing calculator and find the intersection. You don't have to do this by hand. But let's just see if we did this one by hand. Let's say I want to try to get it so that I have both sides having the same base being raised to a power. Well, first things first, I always would have to start by getting that exponential term by itself. That even happens whether I'm doing logs or I'm doing common base stuff. So I'm going to divide both sides by 40. Okay, use alpha y equals. Don't worry about the left-hand side being fractions. You have a graphing calculator, so that should be fine. You'll get 1 over 64 on the left-hand side, and on the right-hand side, you'll have 1/2 raised to the n minus 1. Okay, so if I were to rewrite 64 as like some number being raised to a power, 64 is actually 2 to the 6th. So if I have 1 over 2 to the 6th, hopefully you remember that can be also written as 2 raised to the negative 6. On the right-hand side, if I make this 1/2, 2 raised to the negative 1, raised to the n minus 1. If you have a power raised to a power, they get multiplied. So that becomes 2 to the negative n plus 1 as I distribute. You can now see I have both sides have the same base. I can drop the bases, set the powers equal to each other, and now I'll easily be able to finish solving for n. So a minus 1 from both sides, negative 7 is equal to negative n, or n equals 7. Again, if you don't want to do that by hand, or you'd rather use logarithms or whatever, that's okay. You can use your graphing calculator to find that value. I just thought this was a good opportunity to go back over those exponential expressions. Okay, so all in all, again, sigma is a shorthand way of representing a series, and if you have to write a rule to put something in sigma